Welcome to This Explainer. Today, we are diving headfirst into the fascinating world of reinforcement learning. We're going to demystify exactly how machines learn to master incredibly complex, chaotic tasks completely from scratch, and explore why this specific technology is literally shaping the entire future of artificial intelligence. It's going to be a fun ride, so let's get into it. Okay, let's start off with a massive, head-scratching problem. Computers usually need to be told exactly what to do, line by line. But for chaotic, real-world tasks, like, say, flying a plane through a turbulent storm, we just don't have the exact mathematical answers for every millisecond of flight. There are simply too many variables. If we can't mathematically build that controller step by step from the ground up, traditional programming completely hits a brick wall. We absolutely need a different approach. And that perfectly illustrates the difference between supervised learning and reinforcement learning. Think about supervised learning as having a strict teacher guiding its hand. It's like feeding a system thousands of pictures and explicitly telling it, this is a tank and this is not. But reinforcement learning, our focus for today, operates entirely differently. It drops an agent into a maze-like environment with absolutely zero instructions. It simply sets a target goal and says, hey, figure out how to get there on your own. Section 1. Learning by trial and error. Picture teaching an AI to ride a bicycle from scratch. It starts with a completely blank slate. Step 1, it tilts 45 degrees to the right. To compensate in step 2, it tries steering left. It immediately crashes, receives a sharp negative reinforcement penalty, and learns exactly what not to do. On its next try, it tilts right again, remembers that steering left equals a painful crash, so it tries steering right. Crash again. Eventually, through thousands of these micro-iterations, the system realizes that tilting 45 degrees is just a bad state to be in altogether, and it learns the exact micro-movements needed to never reach that precarious state to begin with. Section 2. The rules of the game. So how does it actually know it's learning? Well, every reinforcement learning system basically leans on 3 foundational pillars. First, it reads the environment. This is the literal landscape or the sensor readings it detects around it. Second, it gets immediate feedback through a reinforcement function. Think of this as the strict thumbs up or thumbs down points it earns for an action. And third, it measures long-term success with a value function. This acts kind of like a telescope, allowing the AI to look past the immediate points and predict its ultimate success way down the line. Now, take a game like backgammon. This is what we call a pure delayed reward scenario. Here, the system gets absolutely zero feedback during play. Nothing. It only gets a 1 or a 0 at the very end of the game. Think about how insanely difficult that makes the AI's job. During the actual gameplay, the AI is completely in the dark about whether a specific move was a stroke of genius or a terrible mistake. This means it has to piece together an entire puzzle of strategy backward from that single final result. To survive and win in these complex environments, the system develops a policy. You can think of a policy as its master rulebook or decision tree, mapping out exactly what action to take in literally any given scenario it encounters. It is essentially the AI's evolving brain. The ultimate goal here is to discover the optimal policy, the perfect set of rules that guarantees the absolute highest possible reward from any starting position it might find itself in. Right, so if the policy is the rulebook, the value function is the scorecard. It calculates the expected total future reward of being in a specific situation. If the AI is trying to decide between 2 possible states, the value function tells the system mathematically which state holds the most promise for long-term success. By checking this scorecard, the AI can confidently choose its next step, wisely, knowing for a fact it's maximizing its ultimate payout. Section 3. How to assign blame. And that brings us to a massive hurdle, commonly called the blame game. If an autopilot program makes thousands of micro-decisions and then the plane tragically crashes at the very end, how does it know which specific action in that massive chain of events to blame? It's incredibly difficult. If an AI performs flawlessly for 5 minutes but makes one fatal error right at the finish line, adjusting the whole system equally would erase all the good learning it did leading up to the error. We need intense mathematical precision to pinpoint the exact moment things went wrong. We actually solve this headache with a clever trick called dynamic programming by pushing blame backwards step by step. First, the system learns to avoid the specific action that caused the immediate crash. Pretty straightforward, right? But over time, it starts assigning blame to the states that led to that action. It learns to recognize the early warning signs of failure long before the crash actually happens. Eventually, avoiding these bad situations entirely saves it from having to crash at all to learn.
Now, to make all this math actually work in reality, we introduce a little something called gamma, which is a discount factor usually set to a number just under 1, like 0.99. This ensures the AI cares slightly more about immediate guaranteed rewards than distant, uncertain ones. Without gamma, in continuous tasks that literally never end, the total potential reward would calculate out to infinity, which completely breaks the math. Gamma gives the AI a necessary sense of realistic urgency, forcing it to prioritize what's right in front of it.
Section 4. Evolving smarter algorithms. As these chaotic environments scale up, basic math just doesn't cut it. Traditional value iteration demands exhaustively checking every single possible future branch. It's incredibly thorough for sure, but way too slow. Alternatively, Q-learning smartly takes a single step sample, which saves a massive amount of computing power. In the wildly complex real world, we simply don't have the memory or the time to calculate infinity. Q-learning gives us a highly practical shortcut. Q-learning is an absolute game changer here. Instead of just asking, how good is this overall situation, it evaluates specific state-action pairs. Think of it like chess. It doesn't just evaluate the layout of the board. It evaluates the exact value of moving a specific knight on that specific board. This allows it to learn the average outcome of its actions without needing the rules of physics perfectly programmed in advance. It figures out the chaos all on its own. But there's a catch. Q-learning starts to really struggle when actions happen milliseconds apart. When decisions are happening at lightning speed, the value difference between one microaction and the next is so exceptionally tiny, it just gets completely lost in the noise. This scaling problem led researchers to develop advantage learning. Advantage learning solves this by zooming in and calculating only the difference in utility between the best action and its alternatives, bringing sharp focus right back to those lightning-fast decisions. Finally, we have TD Lambda. This is a brilliant mathematical shortcut. Instead of the value of a win slowly trickling back one single move at a time, TD Lambda uses an exponential weighting of future states to update the entire timeline of decisions at once. It propagates the truth of an outcome backward from the terminal state to the middle, right back to the start state almost instantly. It vastly accelerates the whole learning process. Section 5. Exploration versus exploitation. This brings us to the absolute ultimate AI dilemma, the trade-off between exploration and exploitation. To find the truly optimal path, an AI must sometimes intentionally choose a suboptimal action just to explore the unknown. It literally risks a penalty, walking away from a guaranteed known reward to potentially discover a hidden treasure chest of better strategies somewhere else. If it only exploits what it already knows, it gets stuck being pretty good, but it will never reach true mastery. Now, here's where it gets really exciting. When we combine this structured trial and error approach with modern neural networks, the whole game changes. We suddenly have the key to unlocking classes of problems that traditional programming could never even touch. Because neural networks allow these algorithms to generalize, they can accurately guess the value of chaotic, complex situations they have never even encountered before. It's a profound leap forward for machine learning. So, this leaves us with one final, pretty mind-blowing thought. If an AI can master the physics of flying a plane or driving a car just by trying and failing in simulated environments, what limits are actually left for machine intelligence? As these algorithms continue to evolve, the chaotic, unpredictable environments we once thought were strictly human domains are now wide open for machines to master. Thanks for exploring this with me.